Alright, so here it says we are going to rework the spring constant experiment we did last fall. So if you remember back during the forces unit, we did a spring lab very similar to this. This will be helpful on the test. The small masses are 100 grams and the bigger ones are 200 grams. And this is a meter stick, so it's telling us in centimeters and we'll have to convert to meters. So the whole stick is 1 meter. Alright, a number of masses stretch out a spring, as shown. Record all the information in the data table. Okay, the first spring has no mass on it, so this is the natural length of the spring, 0.25 meters. Okay, so already we know that the graph down here should not go through 0 because it's already starting out at 0.25 meters. Let's see. It says, then a 100-gram mass is placed on the spring and it stretches. After converting to kilograms, calculate the force pulling down on the spring. Alright, 100 grams is 0.1 kilograms. The force will be the force of weight, which is mass, times acceleration due to gravity, which for here it says it will be 10. So we have 1 Newton. So we can go ahead and fill out. You'll notice that the chart goes 100 grams, 200 grams, 300 grams, 400 grams, 500 grams. Okay, mass in kilograms, this would be 0.1, 0.2, 0.3, 0.4, 0.5. Alright, and then we just multiply by 10 to find the force of weight. So this is 1 Newton, 2 newtons, 3 newtons, 4 newtons, and then 5 newtons. Alright, the natural length is going to be 0.25 the whole time. That's the equilibrium position. It's not going to change. Alright, it wants to know x and the actual position. So let's go through and look at the actual positions here. Alright, for the first mass, which is the 100 grams, we have it stretched out to, it seems like 0.31. So 0.31 meters. And then the 200 gram mass seems to be at 0.35. The 300 grams seems to be at 0.39 right here. The 400 gram masses seem to stretch out to 0.44. And then last but not least, but the 500 grams, notice that it's 500 because it has 2 of the big 200s plus a small 100 gram. It stretches out to 50, so 0.5 meters. Alright, now the x, which is the distance that it's stretched, will be the distance from 0.25. So here, it's stretched out to 0.31, so that's a difference of 0.06. Here we have a difference of 0.1. Here we have a difference of 0.14. Here we have a distance of 0.19. And then the last one is a difference of from 0.25 to 0.5 of 0.25. Alright, so let's write the new position in the table and then measure the distance. Okay, we did all those. What are the units for spring constant? Spring constant is in newtons per meter. Since the slope is always the delta y over the delta x, or change in y over change in x, which spring constant units must be on the y-axis? We need newtons on the y-axis and meters on the x. Alright, it says graph the given data, being sure to label the axes, including with units. Then calculate the spring constant. So we need to go ahead and set up our axes. Since it stretches out to 0.25, we want to make sure that 0.25 is covered here. I'm going to make every 2 boxes worth 0.05. There we go. And then I'm going to make every 2 boxes 1 Newton. Since we go up to 5, everything is covered. Alright, so now we just plot our points. The first Newton is stretched out 0.06, so that's about right here. Newton number 2 is stretched out 0.1. 3 Newtons goes out 0.14, about right there. 4 Newtons is at 0.19. So remember that this is x, the distance that it's stretched. And when we're talking about the spring constant, newtons over meters, meters are the distance that it's stretched out. Okay, and then 5 newtons was stretched out 0.25. So we have these data points. The next thing you want to do is create a best fit line. So we want something like this. And then we want to create or find 2 good points. So this happens to look like a good point, and here we have a good point. Alright, so if we follow that over, that's at 2 newtons and looks to be in between 4 and 5. So this is 4.5 newtons. Okay, so our delta y will be 4.5 minus 2. In other words, 2.5 newtons. Over our change in x, which seems to be 0.225 minus 0.1. So 2.5 divided by 0.225, because it's in between 0.2 and 0.25, minus 0.1. And we get 20 newtons per meter. So our spring constant is this 20 newtons per meter. And that's how you find spring constant with the data and finding the slope.